let's talk about the conservation of momentum. Remember that momentum describes the quantity of motion that an object has. In other words, it describes how easy it is to stop that object. If you got a huge truck with a huge mass, you got a huge truck with a fast move, with like a fast velocity, right? It's traveling down the highway. It's going to be really hard to stop that truck. But if you got a really small toy truck and it has a very low velocity, like a child is just playing with the truck and it's like moving really slowly, it's going to be easy to stop the truck from, let's say, rolling away, right? So that is going to be momentum. Now, we're going to talk more about systems, surroundings, and whatnot. But first of all, the system basically just describes whatever the hell in the universe you're trying to focus on. So let's say in my universe, I got an iced latte with a little bit of ice. And this is my system. So this is just the part of the universe that I'm trying to focus on. If this iced latte is on a table, let's just say, so this is my table right over here. Well, everything else in my universe would be considered surroundings. They're your surroundings. Consider a scenario where you got ball A hitting ball B, and ball B is initially at rest. Now, after ball A hits ball B, ball A turns to rest, so ball A is now at rest, and then ball B now starts moving, right? The conservation of momentum basically states that if you got like a scenario like this, the momentum initially, so the momentum in this scenario, is going to be equal to the momentum in sort of the final scenario where ball B actually starts moving and then ball A is now at rest. Okay, and this is all assuming that there is something known as, this is all assuming that this is taking place in a closed system. Once again, we'll talk more about closed systems later, but just for now, just know that in a closed system, there are no external forces. Okay, and having no external forces is really important because remember from last video, remember impulse is equal to your force multiplied by the change in time is equal to the change in momentum of something. All right, essentially when you apply a force to an object over a certain period of time, that's going to change the momentum. And if you're changing the momentum and everything, then the conservation of momentum isn't really going to hold up, right? Your initial momentum is not going to be equal to your final momentum. However, if you're assuming that there are no external forces, assuming that, I don't go ahead and put my hand here, if this is me right over here, just say this is me, assuming that I don't put my hand here to stop the ball, so then it's also at rest, assuming none of that happens, well, the conservation of momentum is going to hold up. And you can actually see this in, you've definitely seen this before, Newton's credo. So yeah, this one's traveling with velocity and then stays still, then this one stays still, this one stays still, and you can see the conservation of momentum happening right in front of your own eyes, which is pretty cool. Let's say that ball A has a mass of 2 kilograms. And let's say that its initial velocity, so the velocity that it had, is let's say 3 meters per second. Now let's say ball B also has a mass of 2 kilograms. And it's initially at rest, so its velocity is 0. Now, in my second scenario right over here, now ball A has a velocity of, 0 meters per second, right, because it's not moving. And you're trying to find out the velocity, of ball B. So is there a way that we can calculate the velocity of ball B? And I think this formula right over here just really encapsulates what's going on in my diagram. So we know that the momentum, and maybe it's more helpful if I say that the total momentum is going to be equal to the total momentum in our sort of final scenario right over here. So the total initial momentum is equal to the total final momentum. Now the total initial momentum, if we're talking about the total momentum, it's going to be the momentum of ball A and the momentum of ball B, right? And I'm essentially saying that the momentum of ball A from the start plus the momentum of ball B is going to be equal to the momentum of ball A at the end. So this is the end, right? When the balls, hit each other. So this is going to be equal to the momentum of ball A at the end plus the momentum of ball B at the end, okay? And yeah, this is exactly what this formula is saying. Momentum at the start for ball A plus the momentum at the start for ball B is going to be equal to the momentum at the end, right? That's why I put this final velocity here, momentum at the end for ball A plus the momentum at the end for ball B. All right, now let's do this formula. So we know that initially our mass is 2 kilograms for ball A. And we know that it's traveling 3 meters per second. we know that the mass for ball B is also 2 kilograms, and we know that's originally at rest, so the velocity is 0. Now, in our final scenario here, now what happens is that my mass is still 2 kilograms for ball A. Remember, your masses don't change, right? So the mass here and the mass here, the mass here and the mass here, they're going to be the same, right? So we know that mass of ball A is still going to be 2 kilograms, and I know that it's at rest here, right? You can see that ball A has completely stopped. So it's going to have a velocity of 0. And mass B, remember, it's still 2 kilograms. And we're trying to find the velocity of ball B in the end state. So right, this is the end state, and we're trying to find the velocity of ball B. So this is going to be my unknown, right? This is going to be my unknown variable. So we can see anything multiplied by 0, we can just cross them out, and we get that 6 is equal to 2 times the velocity of ball B at the final scenario. And if we divide both sides by 2, we actually get that the velocity of ball B in the ending state, final scenario, whatever you want to call it, that's going to be equal to 3 meters per second. Sorry, I didn't write out the units here, but yeah, velocity is, remember, meters per second. Sticky momentum. Sticky momentum. Kinetic energy is the energy of movement. And when I say that a collision is elastic, so elastic collisions, that means that momentum and kinetic energy are going to be conserved. However, this topic of sticky momentum is actually going to do with collisions being something known as inelastic. Well, perfectly inelastic just means that your kinetic energy in this case is going to be lost. And when we say something is perfectly elastic, that means that we have lost the maximum amount of kinetic energy. Now, you might be wondering, in what world can we have a scenario where two objects, they might hit each other and it's perfectly inelastic? We're losing the maximum amount of kinetic energy. And I'll tell you how that happens. Well, let's say that, once again, we're going to use the same example where you have ball A hitting ball B. But this time, what's going to happen is that ball A is actually going to stick to ball B. So ball A and ball B, you can think about them as being stuck together, and they're just going to move together at the same velocity. So they're going to move together at the same velocity. And that is going to be a scenario where you lose the maximum amount of kinetic energy. And the reason why, now kinetic energy is dependent on both the mass and the velocity. All right, now in a perfectly inelastic collision, the combined mass is going to be heavier. So you can think about these two balls as essentially a single unit, right? Combined mass is heavier. So to kind of conserve momentum, the final velocity has to be smaller, right? It's like if I have the momentum originally, right, and then this is my momentum finally, right? If my mass is bigger, then to make up for that, well, then my velocity has to be like smaller, right? Now, you can see how if you decrease my velocity by even just a little bit, in my formula, velocity is squared. And that means that a tiny change in my velocity will have a big impact on the kinetic energy. So because this one single object right over here is actually going to have a slower velocity than ball A was originally moving, right? The velocity is going to be smaller in order to conserve momentum. Well, with smaller velocity, lower kinetic energy. Now let's try to do a practice problem. 2 kilogram cart moving to the right at 4 meters per second on a frictionless track, and it collides inelastically with a 3 kilogram cart that is initially at rest. After the collision, the two carts stick together. And what is the velocity of the combined carts after the collision? Now, from the momentum formula, from the sticky momentum formula, recall that it's this. It's going to be the momentum of the first object plus the momentum of our second object. That's going to be equal to the combined masses of our objects, right? Because it sort of sticks together. And because the two objects are sticking together, they're going to be moving together at the same velocity. So that's why I multiply both of these terms by the final velocity, because, well, they stick together, right? So 2 kilogram cart, 4 meters per second. 3 kilogram cart, the velocity is, well, it's at rest, so 0. And that's going to be equal to the masses added up, so 2 plus 3, right? That's going to be our masses added up. And then we're going to multiply this by our final velocity, which is what we're trying to find out, right? That is what's going to be our unknown. So we can just do this, and this is just going to be equal to 8, and then we divide both sides by 5, and we get our final velocity, 6 meters per second to the right. Okay, remember that kinetic energy is 1/2 mv squared, right? So our final kinetic energy is going to be 1/2 multiplied by the mass of our final object, which is 5 kilograms, right? And we're going to multiply by my final velocity squared, which is, we calculated that's 1.6 meters per second. 1.6 meters per second squared. Okay, pretty good. Now 1.6 to the second power, multiply this by a little bit of a 5, divide this by 2, and we get 6.4. All right, so my final kinetic energy, you can think about it as kinetic energy final, is equal to 6.4. What's the unit for energy? Joules. Now to calculate the kinetic energy of my initial objects, right? These are my objects initially before they stuck together into like one single mass. So our kinetic energy is going to be equal to 1/2 multiplied by our mass of object 1 multiplied by the velocity of object 1 squared, so 16. And I'm going to add this to the kinetic energy of my second object, right? Because I'm trying to find out the kinetic energy initially for both my objects. So I'm going to have to use this formula essentially twice, right? Because it includes the kinetic energy of this and this. So it's going to be 1/2 multiplied by 3 multiplied by my velocity squared, which is 0 squared. All of these multiplied by 0 just cancel out to 0. So I really don't have to worry about that. And when I actually do the math, I get that, well, 16. My kinetic energy initially is 16. All right, 16 joules. Remember when I said about inelastic collisions, right? When collisions are inelastic, you lose kinetic energy. Momentum is conserved, but kinetic energy is lost because my final velocity is slower than my initial velocity, right? My initial velocity was 4 meters per second. Final velocity is 1.6 meters per second to the right. And in the kinetic energy formula, we're squaring velocity. So velocity is like the big game changer for kinetic energy. And in case of you guys wondering, where did all that energy go, right? Some of the energy was lost as heat, all right? Some of the energy is lost as heat. And in a real world scenario, well, our ground is not going to be frictionless. So some of that energy is also going to be lost in the form of, the friction resisting our objects. Now, you look at the formula for kinetic energy, 1/2 mv squared, 1/2 times the mass times the velocity squared. I get the velocity part, right, because it's dealing with motion, but where does the mass part come in? And to actually understand this, well, we have to connect this to something known as work, which we'll first talk about. So let's define what work is. Work is going to be equal to force multiplied by displacement. So work essentially measures the energy transferred by moving an object with a force, right? And that causes like a displacement in the object, right? So essentially work measures the energy transferred to an object by a force, right? If I'm over here, I got a little box in front of me and push on this box and the box moves. Well, I'm applying a force and the object has a displacement now, right? And energy is transferred, right? Of course, energy is transferred. And so this is just, work is just going to measure the energy transferred through this interaction. So if we were to do a simple example, let's say that this box is moved, let's say 5 meters to the right. And let's say that my force is, 50 newtons. 50 newtons. You would have to just multiply these two values together. So my force is 50 newtons, and I moved it 5 meters to the right. And when I actually do this, so recall what a newton is again. Can anybody recall? Mass is measured in kilograms. Acceleration is measured in meters per second squared. So you just have these things multiplied together. Now, if I multiply this by meters, well, I'm just going to get kilograms multiplied by meters squared divided by seconds squared. This right over here is a new unit, and we call this unit the joule. So in this case, right, 50 multiplied by 5 actually gives me 250 joules. Or I could just write J. Boom. There we go. Okay, so that is how you would write out the units for this. Now, Let's say if this box weighs 2 kilograms and I want to find out the acceleration. All right, just a little quick test. Force is equal to mass times acceleration. I know my force. I know my mass. Solve for the acceleration. Acceleration is equal to 25 meters per second squared, right? Because that's the units for acceleration, and it's going to be to the right, so which we can assume with like a positive sign, right? That means we're just going to move to the right, and boom, there we go. Now, this formula, work is equal to force multiplied by displacement. It's your lucky day. It's your lucky day. It is. It's really your lucky day, guys. So yeah, clap it up for whoever made the reference guide. Now, this formula assumes that the force is actually in the same direction as your displacement, right? So if we assume that we apply a force completely to the right, and this box moves completely to the right, well then, we can use this formula. But imagine a scenario like this. What if I'm punching this box at an angle? So if I punch this box at an angle, well, some of the force will be directed downwards, right? So if I'm doing this at an angle relative to the ground, right, some of the force will be directed downwards. We can say this is the force in the y direction. While some of the force will be directed forwards, and that will be the force in the x direction. Now, assuming if this box is completely on the ground, punching it downwards does absolutely nothing. Like, imagine if my force vector, so remember, force, it's a vector quantity, right? It has a magnitude and has a specific direction. Imagine if my force vector was completely perpendicular to the ground. If I'm trying to punch a box that's already on the ground and I'm punching it downwards, well, the box is just going to stay still, right? Because the box is on the surface. It's not going to move at all. So the only thing that I care about in this scenario is not actually the force in the y direction. The thing that I care about is the force in the x direction, because that force in the x direction is the kind of way that the box actually moves, right? The box only moves in the x direction. It does not move down in the y direction, only moves forward in this x direction. So how can I solve for the x direction? And to do that, we need some trigonometry. So cosine of, in this case, our angle, that's going to be equal to my adjacent side, which is equal to the force in the x direction, divided by our hypotenuse. And the hypotenuse represents our original force. So our original force was 50 newtons, but let's just write F, applied. So this represents our original applied force. And if we multiply both sides by our applied force, this cancels out, and we get that the force in the x direction is equal to our applied force, or whatever force we're actually talking about. It doesn't have to be an applied force, but the force in the x direction is going to be F multiplied by cosine of the angle that the force creates. And then you're going to slap in this cosine of theta term. Theta is going to be relative to our force and essentially the direction that the box is going to. And if you're taking linear algebra, another way to kind of think about this force and everything here is that you can think about work as being equal to the dot product of the force vector and the displacement vector. So we can say that this is the dot product between our force vector and our displacement vector. And you don't need to get into the specifics of that, but the thing to know is that, remember, dot product, the dot product is maximized when the angle between the force vector and the displacement vector is equal to 0. Essentially, if we are punching the box and the displacement is going in the same direction as that force, well, all the force that we use to punch the box is going in straight into the right direction, right? Straight into the x direction. All of our force is being directed into the x direction. And therefore, if you actually look at this formula, that means that the angle between my force and my displacement vector is equal to 0. And you might recall that cosine of 0 is equal to 1. And that's actually the maximum value of cosine. So when our force direction, displacement direction is the same, our kind of work done is going to be maximized. And another thing to know is that, if our force, imagine if we're applying a force, but this time it's going to be perpendicular to my displacement vector. So imagine if I'm applying a force down, even though this box is supposed to be moving to the right or moving to the left, whatever the case is. You notice how it makes like a 90-degree angle, right? when we plug in cosine of 90 degrees in here, cosine of 90 degrees is equal to 0. And therefore, if we multiply anything by 0, so any of these terms multiplied by 0 is still just 0. So you can see how when we're punching this from a perpendicular angle relative to our displacement vector, well, the work done is 0. It's like trying to punch a box. It's like, if I have a box here, it's like trying to punch a box downwards even though it's already on the ground. It's not going to move. And if there's no movement, there's no work done. Another way that work can be defined, if you look at work here, you can see that the net work is equal to the change in our total energy. Now, this is like the work energy theorem. It states that work is equal to the change in our kinetic energy. So let's say if I do some work on an object. This is me. I got a box, and I apply force to that box. And the box starts moving. That right there changed the box kinetic energy. Because I applied a force over a distance, that is going to change the object's kinetic energy, right? Now, it doesn't have to be entirely the change in kinetic energy. As you saw in the reference guide, it can be the change in your total energy. And you'll usually see this, but like, imagine if I started lifting the box, all right, using my hands. Like, just imagine if I lifted the box. And imagine if I'm lifting the box at like a constant speed or a constant velocity. So because I'm lifting the box at a constant velocity, my kinetic energy is not changing, right? Because remember, kinetic energy is equal to mass multiplied by my velocity squared. If my velocity is not changing, my kinetic energy is not changing because the mass, I'm dealing with the same object, right? So the mass is the same. So if I keep on lifting the object at the same velocity, well, my kinetic energy isn't changing. Rather, it's the change in my potential energy. Potential energy is a little bit weird. It's like a stored sort of energy, right? Right now, like if I start lifting the box super high and I keep the box there, the box ain't moving. But like you can think about it as this box has the potential to do work. Because imagine if I let go of this box, what's going to happen? The force of gravity is going to pull my box downwards, right? The force of gravity is going to pull my box downwards. And that means that, you see, my force of gravity is doing a displacement, right? It's doing the displacement, and therefore my force of gravity has done work, right? Or maybe it can be something as silly as, like, y'all ever played with like slinkies before? Like, you freaking stretch out the slinky super, super wide, and you notice it snaps right back. That's actually like another example of potential energy. Actually, in fact, if you go to potential energy here, you can see that potential energy, and you see an S right over here. Now, what does the S mean? The S is a spring. All right, the S represents a spring. The potential energy of a spring is equal to 1/2 multiplied by essentially the spring constant, which just tells you how stretchy the spring is. Strings that might be like a little bit stretchier, that's actually going to have a very low spring constant. So a spring that is not that stretchy, it has a low spring constant. But a spring that is very hard to pull. You can imagine if I have a coil, like like a gravity coil from like Roblox or something, right? Imagine if I have a coil and it's super hard to pull out. So if I actually start stretching this coil, it's very hard for me to do that, but I eventually stretch out the coil super duper wide, and what happens is you'll see it snap back super fast, right? The less stretchy your spring is, the more potential energy there is for the spring, right? Because you need like more energy in order to actually like stretch out the spring, right? So potential energy, it's going to be equal to 1/2 multiplied by how stretchy the spring is, and this is also going to be multiplied by x, which we know is just going to be our change in spring length. It's like the displacement for your spring pretty much. So the potential energy of your spring is dependent on how stretchy the spring is and how much you actually stretched that spring. The more you stretch it, the more potential energy is stored, and if you let go, boom. The harder it is for you to stretch that spring, the more energy you have to invest in order to actually like stretch the spring. And if you invest more energy, right, you're giving the spring more energy. It's like you're giving the spring more energy, and that energy is potential energy. So you're giving the spring more potential energy, and that's actually what allows the spring, when you let go, to go boom, and all that potential energy is going to be converted into kinetic energy. Kinetic energy. All right. So energy is able to convert between different forms, as you can see, right? We went from potential energy to kinetic energy. Think about like solar panels, for example. Like if you have like a solar panel and that thing is facing the sun, you got that thing facing the sun. And we know that the sun has hella energy. So we try to harvest that thing. All right. We're trying to harvest the sun's energy. So you can see that we're using the sun's energy right now for this solar panel, which actually converts this into electricity that you're using to watch the video. Or maybe you're using fossil fuels, using combustion. But the point is that energy can be converted from one form to another. We can establish that. But the thing that's also important is that energy cannot be created nor destroyed. And that is the first law of thermodynamics. Let's say if we have, two cars and they crash. All right. Boom. All right. You guys might be saying, what energy is lost here, right? Because when these cars crashed into each other, kinetic energy has decreased, right? The cars have come to a stop. So we lost kinetic energy. What the hell happened there? Some of the energy is released as heat, right? Imagine like seeing a car crash. Like, I know this is like a little bit like sad, but like, you know how like some race car crashes are so bad that like the whole thing gets lit up on fire, like a fire starts to form. Some of that energy is converted into heat. Some of that energy is used. Imagine this is car A and this is car B. Car A applies a force, right, from the kinetic energy, right? Car A applies a force on this car B, and therefore the car B starts to crumple, right? Whenever, you've seen like a car crash before, you see like the car get like ruined and stuff. Well, it takes energy for the car to get ruined, right? So we're essentially applying a force. So you can think about it as like the car's surface, right? We're applying a force on the car's surface over a displacement. So we're essentially doing work on the car's surface. So let's see another example. Let's say if we throw a ball up. All right, let's say if I have a ball, this is me. Another example would be if I threw a ball up into the air. What's going to happen? Well, the ball is going to get slower and slower, right? The kinetic energy is going to decrease for the ball because the force of gravity is going to pull the object down. So it's going to get to a point where the ball is just going to get slower and slower. However, our potential energy is increasing. All right. The potential energy, that stored energy, is going to be increasing. Whenever something's like increasing in height or something, you should be thinking that object has gained potential energy. Potential energy is actually equal to the mass of your object multiplied by the acceleration due to gravity, which this is a constant. If I go all the way up here, this is acceleration due to gravity. So this is just going to be 9.8 meters per second squared, right? This is how fast gravity pulls you downwards. And so we can just like say this is 9.81 if you want to, but I'm just going to write gravity there. And this is going to be multiplied by the height, of course, right? Because the height of the object influences how much potential energy that you have. The mass of the object also influences how much potential energy you have. Because the thing is that like if the mass of your object is really big, let's say instead of like a toy ball, this was a super big ball. Well, we would need to invest more energy, throwing the ball up, right? And therefore more energy is actually going to be converted from one form to another, right? Because gravity on Earth. Now, I just showed y'all the gravity constant. Well, let's find out why that is. Now, Newton's law of gravitation is this. You have your force. This is Newton's law of gravitation. It's going to be the force of attraction between two objects. It's going to be equal to this constant G, which you can find in your reference table. This should be in your reference table, universal gas constant. And this is going to be multiplied by the mass of the first object times the mass of the second object. And then this is going to be divided by the distance squared, which is, you can think about it as just r squared. This object, if you really think about it, this is kind of wild, right? We're basically saying that every two masses, so if we have like a mass for like an apple, for example, and then this is the mass for me, this is essentially saying that I am attracted to the apple and the apple is also attracted to me, all right? And that's kind of crazy to think about. Every two objects has like an attraction to each other, whether you like it or not. So let's just say that we have Earth and an apple. Let's see if the Earth and an apple have an attraction to each other. So if I use my formula up here, right, this is our gravitational constant thingy. It's 6.674, blah, 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 10 to the negative 11th, right? And then the mass of an apple, let's just say the mass of our apple is 0.2 kilograms. Let's just say that the mass for my Earth, well, it's going to be this, right? And let's say that the distance is going to be this right over here, 6.371 multiplied by 10 to the 6 squared. Remember, it's distance squared. And when we're talking about this distance, we're essentially talking about the distance from the center. All right, so this distance, actually, imagine if the apple was on like Earth's surface. This is going to be the distance from my apple to the center of the Earth. Since my calculator, I get 1.96 newtons. And so you can think about it as my apple is getting attracted to the Earth. So this is like the Earth's, think about it as this is like the Earth's like direction, and the apple is like getting attracted to it. But Newton's third law, every action has an equal and opposite reaction. So if this thing gets attracted to Earth, Earth is also attracted to the apple, and it's at the same magnitude as well. It's also 1.96 newtons. And the math actually checks out for this, right? If we were to find out the attraction between the Earth and the apple, all I would have to do is I would just switch mass 2 with mass 1. Now, this is a little interesting because if Earth's getting attracted to the apple, why doesn't it move? And it's simply due to the fact that, remember Newton's second law, force is equal to mass multiplied by acceleration. All right, why doesn't the Earth accelerate? Well, if I divide both sides by mass, I get that acceleration is equal to force divided by mass. So acceleration is equal to force divided by mass. Now, the apple is exerting a decent amount of force. The apple is exerting a decent amount of force onto the Earth. But the problem is that the Earth is just too damn heavy. Look at how heavy the Earth is. So if I just move this mass into my formula, I'm basically going to get an acceleration that is so small that it's basically negligible. It's 0. However, on the apple's perspective, the apple weighs 0.2 kilograms, right? That's the mass of the apple. So the apple actually does experience a pretty big force from the Earth. The important thing to know here is that the acceleration due to gravity near Earth's surface, it's a constant. That is pretty mind-blowing. Like, think about it. I have a steel ball and I have a regular old bouncy ball. And if I drop them at the same time, they will accelerate to the Earth regardless of the mass. And that's pretty crazy to me. Now, why is that though? Well, the reason why is because even though the steel ball is heavier, right? The steel ball, it's heavier. But if an object is heavier, that means it has more inertia, right? Remember, inertia is like an object's resistance to motion, or of resistance to being put at rest if it's already moving, right? Remember Newton's first law. An object at motion stays in motion, but an object at rest stays at rest. And it's also called the law of inertia because the more the mass, the more the inertia, meaning that this steel ball, if it was originally at rest, it doesn't really want to move, right? So it's gonna build up a little bit more resistance. The acceleration due to gravity is equal to 9.8 meters per second squared. But you might have seen that in this video, I've been writing the force of gravity, and that's a little bit different. The force of gravity is equal to the mass multiplied by the actual gravity acceleration thingy we've been talking about. Now, this force is also called weight, or this gravitational force, this is also called weight. So this right over here, we can call this weight. And the weight essentially represents how strongly gravity pulls on an object. All right. So how strong gravity pulls on an object. And it's equal to the mass of the object multiplied by the gravity due to acceleration. And actually, you know what? I'm going to do the proof. All right. So if we have an object on Earth's surface, right, that's going to experience an attraction to Earth. And we can express this attraction through the force of gravity, right? This experience is attraction from like the force of gravity, right? However, we can also say that, remember our formula, the force is going to be equal to our constant multiplied by our mass of the first object times the mass of the second object divided by the distance from the center of both objects. So we can just set these two equations equal to each other. We can say that the mass multiplied by the gravity, that's going to be equal to all of this right over here, right? And specifically, let's just call this mass 1. Mass 1 represents the object we're focusing on the surface, and mass 2 will just represent the Earth, all right, the Earth's mass. Notice how there's a mass 1 here, and there's just a mass 1 here. So they cancel each other out, right? If we divide both sides by mass 1, they cancel each other out. So we're essentially left with our gravity constant, thingy, due to acceleration, or acceleration due to gravity. That's going to be equal to our gravity constant multiplied by, well, these cancel. So it's going to be multiplied by the mass of the Earth. It's going to be multiplied by the mass of the Earth divided by the distance from that object to the center of the Earth. So I'm just going to say R center of Earth. And then it's going to be squared, right? And the thing is that, you know, we've actually discovered these values, and it just turns out that after we plug in, you know, the mass of the Earth, which I did earlier, and we also, you know, plug in the center, the distance for the center of the Earth, it turns out that we get 9.8 for this G right over here, 9.8 meters per second squared. It's important to point out that the masses of the objects has an influence on the gravitational force. However, the acceleration due to gravity is always constant. And that's what I want y'all to like take away, right? If we have a very high mass, like let's say we have like a steel brick, right? Say if we have a steel brick, it's going to have like a lot of mass, and therefore the force of gravity or the weight of that object is going to be really, really high. All right. However, due to the fact that, you know, the steel thing has more inertia, even though the force of gravity for my steel brick is really big compared to the force of gravity for the small ball, this also has a very big inertia. Let's do a couple of practice problems. Let's say I have a 2 kilogram block and it slides off a frictionless ramp at a height of 5 meters. I want to find the kinetic energy when the box reaches the bottom, and as well as the speed at the bottom. So how do we calculate this? We're going to use the conservation of energy, which tells us that the total amount of energy that I have, right, when the box is on this ramp, that's going to be equal to the total amount of energy when the box is, well, you know, down on this ramp. Now, what is the total energy comprised of? Well, we know that the total energy contains my kinetic energy, which comes from the fact that this block is like sliding down, right? So I'm going to be dealing with kinetic energy, and I'm also going to be dealing with potential energy due to the fact that, well, it's from a height, right? So I know that due to the conservation of energy, my kinetic energy initially plus my potential energy initially is going to be equal to the final amount of kinetic energy that I have plus the final amount of potential energy that I have, right? Now, let's say that we're going to make a little assumption here, and we're going to say that, let's say when we place this block on the ramp, let's say that gravity has not pulled the block down yet. So this block originally, let's just assume it's at rest. All right, there's zero kinetic energy at the start. Now, because this block ain't moving, we don't got no kinetic energy, but we do have potential energy due to the fact that it's from a height. And remember the potential energy formula? Potential energy is equal to the mass of the object multiplied by my gravity acceleration constant multiplied by the height of that object. And we have all these information. We have the mass, we have the height, and we have the constant in our reference guide. And when we actually plug in all those numbers, we actually get a very nice value of 98. And remember, energy is always measured in joules. Okay, so 98 joules. So if I started out with 98 joules, then I can expect that the kinetic energy plus the potential energy at the final scenario, they also add up to 98 joules. That's what I can expect, because we're assuming that conservation of energy, no energy is lost, right? Energy cannot be created or destroyed. Anyways, now let's say that the block starts sliding down. It starts sliding down, and it has reached the bottom of my ramp. It has reached the bottom of my ramp. So notice how the height of this block is now 0. You can see that the height of this block is now 0 relative to the ground, right? It's on the ground, so there's no height from it, right? We can measure the height here, we can measure the height here, but on the ground, the height is just 0, right? Therefore, my potential energy at the final scenario is 0, okay? And if my potential energy is 0, that means that my kinetic energy actually has to be 98 joules. And that's actually a really nice kind of way to do this problem, right? We know that at the final scenario where my block is just moving and it's on the ground, we know that there's not going to be any potential energy. All of that has been converted into kinetic energy. So the potential energy at the start, where there's no kinetic energy, is equal to the kinetic energy at the bottom when there's no potential energy. I know that's like a little bit of a handful there, but just like rewind that part a bit, because that is like a really, really powerful concept that you can use in these problems. Anyways, we want to find out the speed at the bottom of this ramp. So how do we calculate the speed? Kinetic energy, which we know in the final scenario as 98 joules. So kinetic energy is equal to 1.5 multiplied by the mass, which we know is 2 kilograms, multiplied by my velocity squared. So this 1/2 and this 2 cancels out. If we square root both sides, we get that my velocity is equal to the square root of 98. And that number is, let me see, that number is about 9.9 meters per second. 9.9 meters per second. And we're just going to assume that it moves to the right. Like after it goes down this ramp, then it's just going to move to the right. All right. And sorry if I said speed at the bottom. I should say velocity. Kilogram satellites orbit each other at a distance of 10 meters in space. Calculate the gravitational force between these two objects. Well, we're just going to use, whenever we're dealing with gravitational force for any two objects, when we're dealing with gravitational forces on Earth specifically, right, on Earth's surface, then we're going to use the weight formula, which says that the force of gravity is going to be equal to the mass multiplied by the gravity constant for acceleration, right? That's when we use it. That's when we do it on Earth's surface, right? This can be used on Earth's surface, right? However, when we're talking about sort of the gravitational force between any two objects, so not just limited on Earth, any two objects, well, then we would have to use the other formula. So this is like, let me see, this formula right over here with the big G, with the big formula, and my gravity constant is equal to 6 point blah, 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 blah. Let's write that down. I know that my mass for my first object is going to be 1,000 kilograms, and so is the mass of my second object, so I can just write 1,000 kilograms squared. And I just divide it by the distance squared, r squared, which is just going to be 100 meters squared, right? Don't forget that when you're squaring your units, you have to square the units. Like if you have 10 meters and you square this is just going to be 100 meters squared. You're also squaring the units as well, which is very important. Anyways, let's just plug all of this into my calculator. So my force is going to be equal to 6.67 multiplied by 10 to the negative 7 newtons. Another way you might see this on your calculator, for example, if you're doing the calculation, is you might see this E negative 7. All that just means is that it's just 10 to the negative 7, just like a quicker way to write that. Now, let's do this problem, which is a little bit tricky. Now, let's do this spring problem, and we want to find out the maximum kinetic energy of the spring, and we want to find out the velocity of the spring when the spring is at equilibrium. What the spring at equilibrium just means is that the spring is at like the most comfortable position for it. It's not really stretched, nor is it like squished, kind of. Now, here's a pretty crazy thing. Let's say if I stretch the spring, all right? Now, I let go of the spring, and it starts like compressing a bit. When the spring compresses, right, it's eventually going to reach its equilibrium position at some point, right? The spring is eventually going to reach its equilibrium, or it's going to reach its equilibrium position at some point, then it's going to compress, and then it's going to go back, right? Let me just do this example again. You stretch the spring, it reaches its equilibrium position before it compresses, and then it goes back to the equilibrium position. When the spring reaches its equilibrium position here, at this specific moment in time, this is actually when my kinetic energy is maximized. I know that's really weird to think about, but when we want to have the maximum kinetic energy, that's the same thing as minimizing our potential energy, right? Total energy is comprised of kinetic energy and potential energy, like the problem we did before. And let's say if we know that the total energy in my system here, let's just say that's 200 joules. So when we want to find out the maximum kinetic energy, that's actually the same thing as if we try to find the minimum of my potential energy. I know that's really cool, right? If we try to find the minimum amount of potential energy that I have, well, that means I have to have more kinetic energy to counteract that, right? To make sure that the amount of total energy that I have in my system is constant. Now, when you stretch out a spring, that actually increases its potential energy because, well, the spring now has the potential to do work now, to bounce back and everything, right? So when we stretch out the spring, we're actually increasing the potential energy. And same goes when we're compressing the spring. When we're compressing the spring, it also increases my potential energy, because once again, it has the ability to like bounce back and, you know, move and then do work, right? So stretching or compressing the spring actually increases my potential energy. However, at the equilibrium position right over here, well, we're actually going to have the maximum kinetic energy. And that's because my spring is neither compressed nor is it stretched, right? So it has really no potential energy at all. And therefore, all that potential energy is minimized. Therefore, I must have the max amount of kinetic energy. A nice analogy I like to think about is a dude on a swing. Let's say we have a dude, and the dude is on a swing. And when my swing rotates this way, we have potential energy. When my swing rotates the other way, we also have potential energy, right? So when the person, let's say this person is swinging around. Now, at the exact moment when the person sort of reaches the ground, so the exact moment when kind of the swing is in an upright position, my kinetic energy in this scenario is actually going to be maximized, because we have the least amount of potential energy here, right? Anyways, let's try to find out the maximum kinetic energy. So to find out the maximum kinetic energy, we're going to find out the total amount of potential energy that I have. So I want to find out my potential energy and the kinetic energy. Now, if we're trying to find out the maximum amount of kinetic energy I have, what I can first do, it's very similar to the process I did in my first example. I calculate the potential energy I have first when my kinetic energy is equal to 0. Then I know that if I want to maximize my kinetic energy, I can just set my potential energy equal to 0, and then I can get the maximum value for my kinetic energy. So look, my potential energy, remember, potential energy for springs, remember, you got to use a different formula. It's potential energy of a spring is equal to 1/2 multiplied by the spring constant multiplied by the distance from the equilibrium position, so how far you stretched it. This evaluates out to be 1 joule. And all this is saying is that, well, imagine if we have this spring and we completely sort of stretched it out and we sort of held it there. So notice how the spring isn't moving, right? So it's going to have a kinetic energy of 0. However, at this position right over here, my potential energy is going to be maximized with, well, 1 joule, right? We have 1 joule of potential energy. So if I substitute 1 joule into the total energy formula, which comprises of potential and kinetic energy, I get that the total amount of energy in my system is going to be 1 joule. So this total energy thing basically says that no matter if I, stretch the spring or I kind of released it and it starts moving, no matter where I am in this process, I'm going to have a constant 1 joule of energy. In this case, this 1 joule of energy comes completely from my potential energy. Now, if I want to find out the maximum kinetic energy, well, that's just when my potential energy is equal to 0. And we said that when our spring, when we release the spring and my spring reaches this equilibrium position, that's when we actually have a potential energy of 0, right? That's when my potential energy is minimized. And when my potential energy is minimized, well, then my kinetic energy has to be maximized. And notice how if my total amount of energy that I have in my system is 1 joule and my potential energy at this point is 0, well, then my kinetic energy has to be 1 joule, right? Due to the conservation of energy. So that is the maximum amount of kinetic energy that I have. So 1 joule. So if you're able to set one of these energy values equal to 0, for example, if you're able to find a scenario where you can set the kinetic energy equal to 0, and you're able to find a scenario where you can set the potential energy equal to 0, that means that the maximum of your kinetic energy is going to be equal to the max value for your potential energy. So that is an important concept to actually know and apply to these problems. Now we want to find the velocity of the spring when my spring is at equilibrium. So when my spring is at equilibrium, I know that my kinetic energy is 1 joule. 1 joule, right? And so we could just plug and chug into my kinetic energy formula, right? 1/2 mv squared. I know the mass is 0.5 kilograms. And I want to find out the velocity, so v squared. And this is just going to be, this is multiplied out to be 1/4 multiplied by 4, square root that. That's going to be 2 meters per second in whatever direction the spring is going to. All right, now let's talk about this formula right over here. And this formula looks a little weird. It's AC part radical acceleration during circular motion. Okay, I know how that has to do with maybe moving around in a circle. And we have v squared and we have r. Where the hell does radius come into play? And why do we need to find out the radius and why? Okay, I have spun this bug around for a pretty long time, and what I basically done was, okay, so let me stop this here. I basically have this like a wheel thingy, and then I just spin it around. I just spin it around like so, and you can see that now this ladybug is forever going to be spinning. The reason why is because, well, we're assuming that there's no friction here, so it's not going to slow down anytime soon. Anyways, what you notice is that when the ladybug is traveling in a circular path, as you can see, we're accelerating towards the center of our circle. So the center of, the whatever path you're taking, whatever circular path you're taking. You can also see that my velocity is tangent to my circle, meaning that it only touches the circle at one point. And you also notice that my velocity is perpendicular to my acceleration. Now you guys might be wondering, how are we accelerating? Why is there an acceleration vector? Because the thing is that, well, you can see that this bug is just moving at the same speed constantly. So we're not really accelerating. And to counter that, well, we kind of are. And it's a little bit weird. So first of all, we have to take into account that, well, velocity is a vector quantity, meaning that it has, well, a magnitude and also has a direction. So you would say that this velocity vector, where you're going 20 miles per hour to the left, that's different from the velocity vector if you go 20 miles per hour down, right? Because even though the magnitude is the same, we also have to take into account the direction, and the directions are different. Therefore, if there's something causing this vector to change, there must be like some sort of acceleration that's going on. And this acceleration, well, is always going to be sort of pointed towards the center. I didn't draw this the right way, but these actually form 90-degree angles with my acceleration vector. So the acceleration vector is always going to be pointing towards the center. It's going to be perpendicular to the velocity vector. And the thing to know about the velocity vector, I know that's a lot, but the velocity vector is always going to be tangent to the circle, meaning that it's only going to touch one point on the circle. All right. So a tangent to the circle, it would only be touching one point. And then if I draw an arrow here, that would be sort of the velocity vectors for my circle. And then if I wanted to draw if I wanted to draw the direction for the acceleration, it would always be towards the center, and all of these would be perpendicular to my velocity vector. So if I pull up my reference guy here, and I go all the way up here, what this AC is saying is that my acceleration during circular motion, that's going to be equal to my velocity squared divided by the radius of whatever circle I'm looking at. So the radius, this right over here would be a radius of whatever the circle that I'm looking at, right? Because this is the center of the circle, and then my velocity vector, this touches the outer portion of the circle. So this right over here would be a radius, radii, whatever it's called, the circle. Don't worry, I will use like an analogy to kind of explain everything. So also, just to know, force is equal to mass times acceleration. I know that I'm accelerating towards the center of my circle, and therefore there also must be like a force that directs me towards the center of the circle, right? If there's this acceleration, there must be a force. And this force is going to be called... So one example of a centripetal force, and centripetal force is not like a new force. We have seen, like, it's not like a made up force. Like, for example, if we have like our solar system, for example, the sun is in the center, and let's say this is a planet and it's orbiting my sun. It's orbiting my sun in like a circular path. Now, what's sort of pulling this planet towards the sun? And you might be saying, well, gravity, right? Gravity is this force of attraction where that sort of pulls this planet towards the sun. So you can see that even if my planet tries to move off this circle, right? Let's say if my planet tries to move off the circle. So let's say if my planet is here and it tries to move off the circle. Well, then what happens is my sun is going to start using gravity to pull it towards it. So you can see it tries to move this way, but then it ends up sort of bending, right? It ends up sort of curving this way. And once again, it tries to move off the circle again. And keep in mind that if there was no gravity, if there was none of this centripetal force, what would happen is if there's no force directed towards the center, my planet would just drive off straight in a straight line, right there, because there's no force affecting it. But because there's a force affecting it and it's directed towards the center, the planet tries to move off, but it can't. So it's just gonna keep going around in this circle. Another way to think about this is, well, a car, when you're driving a car in a circle, right? So let's say this is like my racetrack, and then this is my car. Now, what's really going on when you turn the steering wheel? In this case, I'm trying to turn the steering wheel to the left. What's really going on there? Well, in a car, let's say this is my car. All right, this is my car. What actually happens is if you're turning the steering wheel to the left, that basically turns the wheels a little bit to the left, right? That you'll see that it turns the wheels a little bit to the left. And what that does is that creates friction with whatever racetrack ground you're on. That creates friction with the ground. And that friction actually pulls you towards the center. So the force of friction would be my centripetal force here. See, it's not a new force. In this case, in the planet case, it would be gravity. But centripetal force is just a force that directs it towards the center. It doesn't have to be like a new force that you haven't heard about, right? It's not a new force. Just force that pulls you towards the center. And from the formula that we've seen in my the acceleration thingy, right? So we know that the acceleration due to circular motion is going to be equal to velocity squared divided by r, and all of that is going to be multiplied. Sorry, not all of that is going to be multiplied, but we know that acceleration. We know that acceleration is linked to force in this formula, right? So if I divide both sides by mass, I get that acceleration is equal to force divided by mass, right? And therefore, I can actually plug in force divided by mass into my formula. So another way I can write this is force divided by mass is equal to velocity squared divided by r. And then if I multiply both sides by the mass, I get that mass multiplied by velocity squared divided by the radius of whatever racetrack you're on. That's going to be equal to the centripetal force. So you can see, if you don't know the centripetal force formula, well, you can just derive it from the centripetal acceleration formula. So this would just be like a classic problem. Let's just say 2 kilogram ball. It's tied to like a string or something, just something like that. And it's like swung in like a circle, right? And it has a radius of 0.5 meters. And it's swung at a speed of 4 meters per second. So how do we do this? Well, you could just use a shortcut version to find the force. So the centripetal force is going to be equal to our mass, which is 2 kilograms, multiplied by our velocity squared. And our velocity is, so 16 meters squared divided by second squared. And that's going to be divided by our radius, which is 2 kilograms. So, sorry, not 2 kilograms, 0.5 meters. And yeah, we could just plug this into our calculator, and we could just get 64. And let's see what units cancel out. So you can see that mass cancels out. So I'm left with kilograms multiplied by mass divided by second squared. And remember that that is actually the unit for newtons. So once again, I should have probably said this earlier in the video, but if you have no idea what you're doing in these problems, just check if your units are the same, or the units are what you expect. I know force has to be in newtons, so if I know the unit for newtons, well, I can just, maybe I don't even have to know the formula. I can just freaking plug it in and see what gives me the right units. So that is the answer. Now, finally, we have this formula. Why do we need to know the circumference of our circle? Why do we need to know maybe the circumference? I don't know, maybe you're given like the area, and you might need to calculate the radius. But there's also another thing that's really important. And that's basically the notion of a period. And this has a symbol T. So period is symbol T. And T represents the amount of time it takes for you to complete one full sort of rotation around this circle. So one full path around this whole circle. That's the period. Now, this formula actually makes sense. The period is going to be equal to 2 pi r divided by our velocity. Now, if my racetrack was super duper big, you can imagine that it's going to take me more time in order for me to circle around the racetrack. Therefore, I would have a higher period, right? That's why circumference is at the top of my equation. Meanwhile, my velocity is at the bottom of the equation, because if I'm traveling faster, right, if my velocity is faster, then it's going to take me less time to loop around this circle. And therefore, my period is going to decrease, right? It's going to take me less time in order for me to make one full sort of rotation. So that is how this formula was sort of created. Now, we know that our centripetal force, that's going to be equal to mv squared divided by r. All right, now we know that velocity, well, we can solve for velocity in this equation. So we can say that velocity equals 2 pi r divided by r, period. All I have done is I've kind of just multiplied both sides by v and then divided both sides by t. So I'm just going to be left with v is equal to 2 pi r divided by t, right? And then I could just make some substitutions into my force formula. So if you're given the period and you want to solve for the centripetal force, well, then that's just like a shortcut way of doing it. But at the end of the day, those type of problems are just like plug and chug. So if you know the main formula for period, you understand how it works and everything, you should be fine. Now let's dive into a little bit more of systems and surroundings. These are just a couple of terms. So when matter and heat can be exchanged from the systems and surroundings, that is an open system. An example of that would be a pot of boiling water. The pot of boiling water, assuming that there's no lid on it, the gas particles can escape, right? Because when water is boiling, of course, you have water vapor, and that causes these gas particles to escape. And you also have heat being exchanged. So that would be an example of an open system. A closed system, well, closed system is when heat can be exchanged, but matter cannot be exchanged. And an example of that would just be our pot of boiling water, except if we had the lid on it. Imagine if I put a lid on my pot of boiling water. Well, guess what? Now the gas particles can escape, but heat can still escape into the surroundings. And really, it doesn't have to be just heat. Maybe I should say energy. So energy or heat can be exchanged. But to make this really simple to understand, I'm just using heat. But just know that if any energy or heat can be exchanged, but matter cannot be exchanged, well, that's a closed system. And then finally, you might have guessed it, an isolated system is when neither matter nor energy can be exchanged. So an example of that, theoretically, like a thermos. Have you ever seen like a thermos bottle? One of those like fancy water bottles that keeps like the heat perfectly trapped inside, ideally, so that if you're in like the Arctic or something, and then it's really, really cold, you're still gonna have hot water with you because it's being trapped inside this thermos. So that is going to be our isolated system. What does it mean to be powerful? Power is defined as how much work you do divided by the amount of time. All right. So let's say that you've done 200 joules of work, and let's say that it takes you 2 seconds to do that. The power of that would just be 200 divided by 2, which is 100 joules per second. All this is saying that every second that passes, you're doing 100 joules of work, right? Now, imagine if I took less time to do this, right? So imagine looking at this equation, right? You can see that if the amount of work that I do increases, my power increases, right? And that makes sense, right? If I bench press, let's say 10 pounds, well, I'm going to be using more power than if I bench, let's say 5 pounds, right? With the same height, assuming the same height and everything, right? That's going to require more work for me to bench the 10 pounds. And likewise, if I bench 10 pounds, let's say in 2 seconds, that's going to be more powerful than if I bench 10 pounds in 4 seconds, right? Because it took me less time in order to do that, well, more power, right? So all in all, power essentially just measures how fast are you doing work, right? It's work over time. How fast are you doing work? Now, I know this is like a long chain of formulas, but luckily the reference guide has it. We know that work is equal to force over force multiplied by displacement, right? So I can say that power is equal to force multiplied by displacement divided by time. I also know that displacement divided by time is equal to my velocity. So I can say that power is also equal to force multiplied by velocity. So these are, 4 totally valid, power equations that you can use. And if you're trying to do a problem like this, it's just knowing like which formula to use in your reference guide. Now this is actually more of like a chemistry topic. Q is equal to MCAT. Heat, which is the symbol for Q, that's going to be equal to the mass of the object multiplied by the specific heat capacity of the object multiplied by my change in temperature. Change in temp. All right. Now, what this formula is used for is you're trying to find out how much heat does it take for me to raise an object's temperature by some specific amount. So let's say if I have like a metal fork, for example, right? Let's say if I have a metal fork. all right? And I'm trying to raise the temperature of this fork from, let's say, 10 degrees Celsius to 20 degrees Celsius. Well, how much heat does it require to do that? And you're going to use this formula. You can see that the amount of heat required to do this process, to raise the temperature of something, this is dependent on how the mass of the object. So imagine if I have like a really big fork, all right? Instead of dealing with this mini fork, imagine if I'm dealing with like a super big fork, a spork, all right? This is my super big fork. Now, obviously, it's going to take much more heat to raise the temperature of this big fork from 10 degrees Celsius to 20 degrees Celsius, right? So, of course, mass is an important factor in determining how much heat is needed for that. Another important factor to consider when we're talking about how much heat is required to raise from this temperature to this temperature, well, we have to consider how easy the object actually changes temperature in the first place, right? So basically, the type of object that it is. For example, if you're dealing with a metal object, metal objects usually require less heat in order to raise its temperature. All right. And you would say that the specific heat capacity for metal objects is going to be pretty low, as a low specific heat capacity, because it does not take that much heat in order to raise the temperature of the metal fork. Remember, metals, they're really good at absorbing heat, which means that the temperature is going to rise really quickly, even with just a little amount of heat. Meanwhile, if we have this piece of glass right over here, this piece of glass is very bad at absorbing heat. Therefore, in order to raise its temperature by a certain amount, it's going to require more heat. So it's going to have a high specific heat capacity. All right, it's going to require more heat in order to raise the temperature of that object. And finally, we have to consider the change in our temperature. If we're trying to change the metal fork's temperature by, let's say, 10 to 20 degrees, well, that's going to take quite a bit of energy, okay, or quite a bit of heat. But if we're trying to change the temperature of the fork from 10 degrees Celsius all the way up to 1,000 degrees Celsius, of course that's going to take more heat, right? We're trying to raise the temperature more. Well, if we're having a bigger change in temperature, that's going to require more heat. So therefore, a change in temperature is also an important factor too. Let's say if we have some water, we're trying to raise it from 20 degrees Celsius to 60 degrees Celsius. The mass of, my water is going to be 0.2 kilograms. And the specific heat capacity of water is 4.184 joules divided by grams multiplied by Celsius. All this is saying is that if I want to raise 1 gram of water by 1 degree Celsius, that's going to require 4.81 blah, blah, blah joules, okay? Now, whenever you're dealing with heat, this Q right over here, remember, heat is energy, and energy is always measured in the units joules. So I have to make sure that whatever calculations I perform here, I'm going to end up with joules. Now, the problem with just plugging and chugging into my equation now is you have to check the units, all right? This specific heat capacity is saying that I need this much energy to raise 1 gram of my water by 1 degree Celsius. However, my mass is in kilograms. That's no good. What do I do? Well, the thing to know is that, you also have your reference guide for this, which is actually really nice. So when you're talking about a kilo of something, that's 10 to the third of whatever the regular unit is. For example, if you have like a gram, well, then a kilogram would just be 1,000 grams, or 10 to the third grams, right? So you can say that, if we have 1,000 grams, then that's the same thing as 1 kilogram, right? Notice how the grams cancel out, and I get that. My specific heat capacity is going to be this: 4,184 joules per kilogram, or 1 degree Celsius. That makes a lot more sense. Now the kilograms are matching, and I can just plug and chug into my formula. So this is my specific heat capacity. This is my temperature change is 40 degrees Celsius, right? My change in temperature is 40 degrees Celsius. And then my mass is 0.2 kilograms. So I literally just plug everything into this formula, right? And then if I'm doing the calculations, all right, and I get this for my answer. And I also want to take a look at how this kilograms cancel out and the Celsius cancel out. So I'm left with the units joules, which is the energy unit, and that's exactly what I was hoping for. So this is a classic problem. I'm going to go over some Regents problems. And here's the first one. And take some time to maybe think about this one for yourself and maybe answer it. All right, so we know we got a pendulum, and this is our ball thingy. And it goes from point A to point B to point C. And we want to compare the kinetic energy from point B to point C. Now, when the ball is at rest, right, before it is even dragged down by gravity, let's just say that the ball is at like point A, right? It started out from point A. At point A, this is when we have the maximum amount of potential energy, right? Because the ball ain't moving yet. And this is when we have the lowest, or you can say this is when we have the minimum amount of kinetic energy, right? Now, notice point B right over here. Point B, it's in the middle, right? Point B is literally in the middle. We are in the middle of our, well, falling down portion. So this point right over here, point B, is actually when we have half and half. This is when we have half potential energy and half kinetic energy. So we have half potential energy and half kinetic energy, right? And all right, so there we go. And we know that it has to have half the potential energy because look, the height of this thing is 0.8 meters, right? But at point B, the height of this is 0.4 meters. So we're going to have half the potential energy and we're going to have half the kinetic energy as well. And finally, at point C, we're directly on the ground. So we have no potential energy at all on the ground, but we're going to have the maximum amount of kinetic energy. If we have half the amount of kinetic energy, you can think about that as 50% at point B, right? And you can think about it as point C, well, we have 100% kinetic energy and 0% potential energy. So notice how this is a 2 times increase, meaning that twice as great is our answer. Okay, so now we have this problem, 75 kilogram student, and given all this information, we're trying to find the average power. So we aren't given the displacement, right? We're given the displacement, right? And we're also given the time, and we're trying to calculate power. So it looks like the easiest formula to use is power is equal to force multiplied by distance divided by time. Now, what exactly is the force in this case? Well, let's say you're trying to run up some stairs, right? If you're trying to run up some stairs, you have to counteract gravity, right? Gravity is going to act downwards, right? And the force of gravity, we know that the force of gravity is equal to your mass multiplied by the gravitational acceleration constant, right? That is all the way here, right? So essentially what you have to do is you have the force of gravity acting down on you, and what you got to do is you got to counteract that with a force that's essentially equal to this. If I want to find out the force of gravity for this person, well, then it's just going to be 75 multiplied by the gravity acceleration constant, and 75 multiplied by 9.8 gives me 735, so that gives me 735. And if I just plug all my information into this formula, I know my force now is 735 newtons. I know that my displacement is going to be 13 meters, and I know that my time is going to be 25 seconds. Plugging this into my calculator gives me about 382, which matches up with answer choice number 30. Finally, we have this problem right over here. So we're given a table. We have a mass of 2.8 kilograms, and this shows the train's momentum during the first 4 seconds of its trip. And we want to plot the momentum versus time for the first 4 seconds of the train's trip. So I did that in Desmos, plugging in all the points. And the next thing to do is we want to draw a line of best fit line using a straight edge. Once again, I'm doing this on Desmos, so if you're doing this in person, just make sure that you're not drawing like a curve or anything. And finally, using your best fit line, determine the average force acted upon the train. Now, this is actually something that's really important to know, is that remember this formula where you have F net multiplied by your time is equal to mass multiplied by the change in velocity. It's given to you on the reference guide, but kind of the full formula is that your force multiplied by your change in time gives you your change in momentum, right? Now, if I would divide both sides by my change in time, I get that my force is equal to my change in momentum divided by my change in time. And take a look at what's happening here. Momentum is on the y-axis, right? Because, well, this is the x. Time is always going to be x, and momentum is going to be y. So you can see that this is our change in y over change in x. And essentially, the slope of our line, so the slope of this momentum versus time line, essentially tells us our average force. And what is the slope of our line? It's approximately 4.433333, right? So that is going to be our average force. Now, of course, maybe on the actual exam, right, it's not going to be, you're not going to be as exact, and that's completely fine. Maybe you got 4.4 or, something like 4.5 instead, newtons, right? That's completely fine. Anyways, calculate the magnitude of the average acceleration of the train, and we want to show all work, including the equation and substitution with units. Okay, Once again, force is equal to mass times acceleration. We're trying to solve for acceleration here. We know our force is 4.4 newtons on average, and we know that the mass of our object, it says it here, 2.8 kilograms. And this is just going to be simple division. And when we solve for acceleration, I got that my acceleration was 1.57 meters per second squared for my acceleration. So that is going to be it. Thank you guys for watching the video. I hope you enjoyed it.